Alright, good afternoon. We continue on scheme analysis. So any question before I start? Alright, we did I reviewed driving the shear force diagram and bending moment diagram for this simply supported beam when we have concentrated load. So let me look at a beam with, we are just reviewing, we don't, I haven't started yet talking about the new material. So what if we have a distributed load, something like this? With the load density of Q. The unit of the Q, a load density, the unit is Newton per meter. So just imagine, put a weight on the top of the beam, it's gonna be type of distributed load. We would like to find shear force diagram and bending moment diagram for this type of the problem. So the first thing that we need to do is finding reaction force, R1 and R2 at two ends. If the length of the beam is L, I can, to find R1 and R2, I can replace the original beam with something like this with one force applied at the middle. And what would be the magnitude of the load is going force is going to be Q times L. Q times L. So to find R1 and R2, I can do that. Replace this with this simply supported beam with one concentrated load with the magnitude of Q times the length of distributed load, which is L. So now by looking at this, you can find R1 and R2. You can write two equations. One is the summation of the force, the other is summation of the moment about either point A or point B equals to 0. But since we have symmetry, I can say R1 is taking half of Q times L, and R2 is getting the other half. So I know this. Then I can start looking at the shear force diagram and bending moment diagram. We start from a starting point, which is A. The only force that we have, or the only load that we have, is this distributed load. So it means I only have one section. So if I cut the beam at the distance of X for once, I can get the shear force diagram and the bending moment diagram. So I cut it at this location, which has X. So if I draw this, the section that I cut, I will get this distributed load with the load density of Q represent shear force and positive bending moment. I'm looking for V and M. One more time, I replace this with something like this. The load density is Q, this distance is X, the magnitude of the load is Q times X. Now I have the standard form of section that I cut. I can write sigma F equals to 0, negative R1 and negative Q times X, positive V equals to 0, this is positive R1. So positive R1 minus Q times X plus V equals to 0. V is gonna be Q times X minus R1. And R1 is Q times L divided by 2. I just plug in Q times X minus Q times L divided by 2. Good?
Why is V positive?
Again, my dad. Thanks for catching. V, it goes down. So V is gonna be R1 basically minus Q times X, or Q times L over 2 minus Q times X. Thanks for catching. Any question on this? So we said the summation of the moment about point A equals to 0. Why it's equals to 0? Because it's not rotating about point A, and point A cannot support any moment. So it tells me the summation of the moment should be equals to 0. This force, it doesn't make any moment at this location because the distance from point A is 0. This force is making Qx times X over 2. This is X, half of the, this section is going to be X over 2. Qx times X over 2. It's making clockwise, which is negative sign. So negative Qx times X over 2. This V times this distance is making, again, clockwise, which is negative. Negative V times X plus this M, which makes counterclockwise. M equals to 0. So then M is gonna be Q x squared divided by 2, Qx squared divided by 2, plus V times X. What was the V? Qx squared divided by 2 plus V times X. I multiply this by X. Plus QL over 2 times X minus Qx times X, which is Qx squared. I have negative Qx squared, positive Qx squared divided by 2. I will get QLX divided by 2 minus Qx squared divided by 2. Or I can say M would be, just take Qx divided by 2, L minus X. Any question on this? Now, if I ask you to draw the shear force diagram, this is V, this is X. This is the equation that you should draw. It's a linear function, as you see. It's V is a linear function of X. So at X equals to 0, a starting point, I will get V equals to QL over 2, positive. At QL divided by 2. At X equals to L, I will get QL divided by 2 minus QL. Which is negative QL divided by 2. negative QL divided by 2. It's going to be this board, connect these two, you will get something like this. This is shear force diagram.
I have a question.
Yes.
In the sum of the moment at A equals 0, it says equals negative. Is that QX times X over 2? Or
This one?
no, the one above it.
Yeah, yes. Negative QX times X divided by 2.
Okay.
This is the distance, and this is the magnitude of the force. Qx times the distance, how much moment is making? And does it make sense? I mean,
Yeah, no, I couldn't read it.
okay. Now let me draw a bending moment diagram. If you look at this, it's a quadratic equation. At x equals to 0, m should be equals to 0 because point A cannot support any moment. And if you plug in x equals to 0, q times 0 is going to be 0. And at x equals to L, also we expected to get m equals to 0. X equals to L, you will get 0. So if you got something different, means you have made this. Then it's gonna look like this. A quadratic function passing through the beam. So now if I ask you what would be, where it's going to be the critical section, by looking at the bending moment diagram, you will see the middle points of the beam is going to see the maximum moment. M max occurs at x equals to L over 2. So if you are looking for the magnitude, just plug in x equals to L over 2, you find the magnitude of the M. So, based on the shear force, either a starting point or the ending point of the beam would be the critical section. But if you remember, I said almost all of the cases we just look at bending moment diagrams to find the location of the critical section. Critical section is located at x equals to L over 2. So the middle point of the beam is, if the failure occurs, it's gonna happen at the middle point. And we should do the design or analysis at the middle point of the beam. Any question on this? All right. I didn't. We might have ramp as a distributed load, something like this. I didn't work on this problem, but you have seen this in mechanics of the material course. The idea would be the same, just different calculation. All right. Before I show you the toolbox of BMD on MATLAB, let me talk about this. So if we have this beam which is located on plane X and Y, it's located on this plane. If I ask you what would be the direction of the shear force, you can see the shear force is a vertical, so V is gonna be in Y direction. And if I ask you what would be the direction of bending moment, then you can say these forces, they are going to rotate the beam or making the moment of the beam. It's about the axis coming out of the plane, which is the axis. So on XY plane, we have M about Z axis. Shortly we will see the problem with forces acting in different plane, and the question is how can we find the critical section for those problems. We will look at them shortly. So. All right. Consider this shaft and pulleys. There is a shaft, and these are two pulleys. These pulleys, this pulley has been connected by belt to the motor. So the motor is gonna run this pulley via the belt. The motion and the torques coming from the motor, and it's gonna be transmitted to this shaft, to this pulley, and via this belt, it's gonna go out. So basically, this shaft and the pulleys, they are going to change the direction of the motion from this direction to this direction. They are going to transmit the torque and power from the motor to somewhere else. So this shaft is acting like a beam because the bearings, they are going to support the shaft. So it's kind of a beam. So with two supporting point. The motor is making tensile force in the belts. Here, the force that we are gonna see on the belt is 200 pounds. Right here, we are gonna have 1,000 pounds on the belt. So the diameter of pulley B is 4 inch, and diameter of pulley C is 8 inch diameter. So before we go further on this problem, let's talk about second Newton's law. So second Newton's law says force equals to a mass times acceleration. So it's for translational motion. So if one rigid body gets some force, it's gonna have acceleration on the motion. But if one rigid body is moving at the constant speed, then acceleration is gonna be 0. So summation of the force applied to the rigid body should be equals to 0. This Newton's law has the rotational equation as well. Alpha is the angular acceleration. I is the mass moment of inertia of the rigid body. And T is the torque. So the total torque applied to the rigid body is going to be equal to the I times alpha. So now if I tell you one rigid body is rotating at the constant speed, constant omega rotational speed, then you can say alpha is going to be 0, then the torque should be equal to 0. Summation of the torque should be equal to 0. So now back to this problem. The motor is going to have the input torque. So the torque is coming through this pulley, and we know that this driving shaft is rotating at the constant speed. It tells me whatever torque is coming into the shaft should go out at pulley C. So T in should be equals to T out. Then it's gonna be the summation of the T equals to 0, then omega would be constant. If it's not true, this shaft is gonna speed up because of the acceleration. So now we would like to find, I can check this for you. If this 200 and this 1000, this 200 times the radius is making torque, is gonna rotate the shaft. So T input is gonna be force, just put your finger in the direction of the force, times distance is making torque in this direction, in X direction. It's gonna rotate it in this direction. So which is gonna be positive direction of X. So T in is gonna be positive 200 times the diameter of pulley B. This 1000 is making opposite direction. It's making rotation in opposite direction. 1000 times half of the diameter, which is radius. Force times distance is making rotation. The output. This 500 is making positive because it's making counterclockwise rotation, or it's making my thumb is gonna be in X, positive X direction. So 500 times the half of diameter of pulley C. Positive 500 times DC divided by 2. The other one is negative 100 times BC divided by 2. So dB is 8. It's going to be 200 minus 1000 times dB divided by 2, negative 800 times the diameter of pulley B is 4 inch. 4 divided by 2 to negative 1600. We should get positive 1600 here, then the summation is going to be 0. If it's not, then summation of the torque is not 0, it's going to accelerate. 500 minus 100 times BC divided by 2. 400 times 8 divided by 2, which is 4, 1600 pound inch. The unit of the torque in US system. So as you see, the input torque plus output torque, it's going to give me 0. So I could remove this 100 and asking you what should be the tensile at this side of the bells. You could calculate for this 100, or I can remove any of those tensile forces on the bells. By setting up this equation, you can solve for that. But here I just showed you that it should be valid. All right, back to our problem. So I have these two forces, 200 and 1000. 200 and 1000, which totally means 1200. Applied at point B in the direction of Z. So if this is axis Z and this is axis X, I'm looking from the top. Axis Z and axis X. I'm looking from the top. What I see is axis Z and axis X. At location B, I'll see 1200 pound pointing down. What else? There is no other forces in Z direction. I see the summation of this force acting in Y direction. So if this is Y, this is X. I'm looking from this view, Y and X. I will see 600 applied at location C, A, B, C, and D. So this 1200, it occurs at plane ZX, This force which acting in plane ZX is making moment about Y. It's rotating the moment, the beam, it's gonna rotate the beam or the shaft about Y axis. And here this problem, this part, it's acting on plane XY, which makes moment about Z axis. So I should look at them separately. So on plane X and Y, as you see, we have 600 pounds. And if I want draw the bending moment diagram for that, we know how to do that. X is the length of the beam, and this is going to be mz, moment about z-axis. If I do before I get to this point, I need to find the reaction. I'm looking at this. I have a beam with 600 applied here. I'm looking for R in Y direction, R1 or RA, and R and BCD in a Y direction. Summation of R should be 600 pounds. This 600 times this distance, which is 20, is making clockwise, which is negative. So negative 600 times 20 plus this times this distance is making counterclockwise, which is positive, and the distance is 30, 10, 20, 30. The entire of the shaft is 30 inch. Set it equals to 0. We can find RD Y equals to 12,000 divided by 30, which is going to be 400 pounds. 400 pounds goes here. What is left? 400 plus 200, it goes right here. Then I will look at the beam. I start from here. I label this as section 1. It goes up to the first point, the first force that you will see on the beam. And after that, we are going to have the second section. We cut it at the distance of x. 200 here. This is x. This is v. This is m. Solve for v and m. Positive 200 minus v, set it equals to 0, v equals to 200 pounds. For the m, just write v times this distance is making clockwise, which is negative. Negative v times x plus m equals to 0. M would be v times x, and v is 200. 200 times x. For section 1, this line is 200 times x. At x equals to 20, 200 times 20 is going to be 4,000. 4,000. At this point, point B, 200 times 10, we will get 2,000 as an MB. Right, the bending moment for the section that you cut here, you will get this line. So we are done with the XY plane. Now we look at this plane, plane XZ. Plane XZ is making M with respect to Y. Same logic. I have 200 pounds applied here. What would be the reactions here? R in Z direction at point A. What would be the R at Z direction at point P? If we write the same things, we will get 800 and 400. And for the M, we will get 800x for this. I just skip the process because it's going to be the same. M would be 800 times x, which means M in y direction at point P is going to be 8,000, and here it's going to be 4,000 if we get the line equation for M. Now we are done with the process, but the question is which section is going to be the critical section based on the bending moment. If you look at the MZ, only MZ, you can definitely say that section C or point C is going to be the critical section. But if you look at MY, point B or section B is going to be the critical section, and if the failure wants to occur, it should occur at section B. But how can we answer? How can we come out with one critical section? MZ and MY are two vectors. MZ means bending moment about z-axis, and My means bending moment about y-axis. So z and y-axis are perpendicular to each other. As you see, z and y are perpendicular to each other. So what I can say, z and y, I can say that summation of the moment is going to be mz squared plus my squared. So then what I'm going to do, I'm going to find the magnitude of the m at point B and point C, then compare them. M at B is going to be a square root of 8,000 square plus 2,000 square. Whatever is the mz is coming here, whatever is the my is coming there, and m at C is gonna be, this is 4,000. This is 4,000 square plus the other one also is 4,000. Compare these two values and come out with critical section. I guess point B is gonna, section B is getting the greater value. Section B is the critical sections, yes. So we do the design or analysis for that point of, for pulley B. If you want to design the shaft, we are doing for point B. It's very important example because when we cover the S stress on the beam, we back to the same example to find the S stress at the critical section. So I just work on the first half of the problem by finding the location of the critical section. Now I need to find the S stress at this critical section, or if I need to design, I should do the stress analysis before I go to the design part. Any question on this problem? All right, let me show you the toolbox that you may need for the coming homework. So if you just type BMD underline tool after you put the MDT folder on the path of the MATLAB, you come out with this window. It's starting with the beam length. So you need to define whatever is the length of the beam. I'm just entering the numbers that we got from the examples that we did in the class for uh, 20 inch. As you see, it has 20 inch length. Just enter 20 inch. Next line, number of loading. Do we have any external moments applied to the beam? If you look at this, there is no external moment. We only have force and just concentrated force. We don't have any distributed load as well. So how many force do we have? 1, 2, 3, 4. 4 distributed load. So back to the box. No moment, but here you pick 4. If you pick 4, it's going to ask you the magnitude and the location of the forces. On the first window, you just enter the magnitude. If it goes up, put positive. If it goes down, put negative. R1, I guess it was 210. Just writing here. R1 is positive 210. The second force is negative 200. Third force is negative 100. And last one is positive 90. So I'm going to enter 210. Negative 200, negative 100, and positive 90. And the next one, just enter the location. So the location of the forces. The first one is acting at 0, second one at 4 inch, 10 inch, and the last one is 20. So I enter 0, 4, 10, and 20. 0, 4, 10, 20. So there is no other force or no uniform step or no ramp. Uniform step means distributed load. So if you just click on draw, you should get, hopefully, the shear force diagram and the bending moment diagram, and it tells you the maximum bending moment diagram. Maximum bending moment occurs at x equals to 10 with the magnitude of 900, and the Vmax is going to be at this location. Before we leave, if we have distributed load like this, suppose Q is 50 and the length of the beam is 10. 10 times 550 is going to be 500. Divided by 2 is going to be 250. So we have two reactions here. Here. So the beam length is going to be 10. We don't have any external moment, but we have two forces. These two forces. This is distributed load. With the magnitude of positive 250, another positive 250, the location would be 0 and 10. And we have one uniform steps. The first one is asking you for the density of the load density, which is negative 50 because it goes down. Don't forget about negative. Negative 50 because it goes down. And second one is asking you at which point it's going to start. The distributed load that we have, it's going to start at 0. So then you will get something like this with this value. Just think about what if I have distributed load just for 4-inch. How can I enter the numbers for that? Because if you enter location 0, it's considered entire of the distributed load for entire of the beam. What if I have only for 4-inch? What can I do for this type of the problem? We enter one entire like this and another one opposite like this. So you enter two distributed load. One is starting from 0, the other one is starting at 4 with the negative sign. It's gonna cancel out this and you will get on the this. Alright, I will collect the homeworks and I will post